Hello and welcome back to Diksha Karnataka YouTube channel, and you are watching second PU midterm revisions of physics chapter current electricity. I have already done 2 lectures on theory revision as well as MCQ revision. Now it's time for me to discuss all the 2, 3 and 5 marker questions that are important from this chapter, including numericals as well as derivations. Everything will be covered in this lecture, so don't go anywhere. Watch till the end, and if you have not yet subscribe to our channel, don't forget to subscribe to our channel and obviously join the WhatsApp group. The WhatsApp group link is given in the description of this video. And also one more request, share this video with your friends and all the classmates that with whom you are studying. Growth of the channel is very important to maintain for the future content. Now let's start with the first question. Let us discuss the questions that I am going to discuss in today's video. So I am going to discuss 5 2-marker question, 3 3-marker question, 3 5-marker derivation, and that's it, that's enough, and 5 numerical questions. Now numerical questions obviously is not predictable, cannot be predicted exactly, but the pattern questions and the style of questions generally remains the same. So I am going to discuss few of the most commonly asked question. Now let's see 2-marker question. First question: define drift velocity and mobility of free electrons in conductors. Or this is a question. The question can be asked in 2 ways. Either they will directly ask define drift velocity and mobility, or they might ask define mobility and mention its unit. Both are common and very often asked. Let's see. Drift velocity is the average velocity with which the free electrons drift under the influence of an electric field. Very important to remember that it is under the influence of an electric field and it is called drift velocity. Now mobility of free electron is defined as the drift velocity of electron per unit electric field applied, right? So drift velocity mobility is basically mu equals to Vd divided by E, only the magnitude. So this is the mobility, and unit of mobility is meter square per second per volt. Very important to remember, meter square per second per volt, or meter per second per Newton and into Coulomb. So whatever formula you are comfortable with, you can use that. This is the simplest formula, and you have to remember that mobility is given by magnitude of drift velocity divided by electric field. Now drift velocity is meter per second and electric field is Newton per Coulomb. So you can write meter per second Newton per Newton, and Coulomb is in the division, so it will go up and become +1. So this is how you can write the unit as well. Now let's move on to the next question. Mention 2 limitations of Ohm's law. Very common and mostly asked across different districts. The same question is asked. Ohm's law is applicable only for all physical conditions remain same. Okay, Ohm's law is not applicable at very low and at very high temperature. Ohm's law is not applicable to non-ohmic devices such as semiconductors, discharge tube, etc. So this is very common. Any 2 limitations are sufficient. So very high and very low temperature, Ohm's law is not valid, and obviously the physical conditions has to be the same, has to constant, so that you can apply Ohm's law. Give any 2 differences between current and current density. Current is denoted by, of course, I, and current density is denoted by symbol J. Now that is not a difference, by the way. I have seen students write that current is denoted by symbol I, current density is denoted by J. That is not considered to be a difference. Unit can be considered as a difference, but not the symbol. So current is defined as the amount of flow of electric charge per unit time. Current density is the amount of current per unit area. Unit of current is ampere. Unit of current density is ampere per meter square. Okay. name two factors on which the resistance of a metallic wire depends. So resistance of a metallic wire is directly proportional to the length of the wire, and resistance of the metallic wire is inversely proportional to the area of the cross section of the wire, right? So these are the 2 points that you have to mention. You can mention L is length of the wire, okay, and area is the area of cross section of the wire. Okay, if you mention these two, you will get full marks. Now let's move on to the next question. Write the expression for drift velocity in terms of current. Explain the terms used. So current is basically N E A V D, and obviously N is number density of electrons. What is number density, by the way? Number density means number of electrons per unit volume. Okay, E is charge of an electron. Okay, A is area of cross section, and Vd of course drift velocity. Vd is drift velocity, right? So this you have to mention the equation, and then you have to mention the terms as well. So this is how you can score full marks. Now let's move on to the next question. Derive the expression. Now this is a 3 marker question. So far whatever questions we have discussed are 2 markers. Now let's see the 3 marker questions. Derive the expression for current density in terms of electric field and conductivity of the material starting from drift velocity. So from where you are starting is very important to remember. Okay, the same question can be asked in 2 ways. I think the next question is the other form, but first we will start from drift velocity, that is I equals to NEA VD. Okay, so this is the starting point, and we have to find the relationship between the current density and electric field. In back of your mind you should remember that J equals to sigma E, that we are trying to prove. Okay, now so what is J, by the way? J is given by I by A, current divided by area. So what is that expression is? From here we get NEVD. Okay, NEVD, right? Now you have to substitute here the value of sigma and E. Now sigma is conductivity and Vd is drift velocity. So you can remember one shortcut over here, that Vd can be written as sigma into E divided by NE. Okay, this is the shortcut substitution that you can remember. If you put the value of Vd, Vd has an expression, sigma also has an expression. If you compare this and simplify that, you will get this expression. So this is how you can simplify the answer. No one going to stop you if you answer it like this. Okay, but remember that you have to mention that Vd equals to sigma E divided by NE. Okay, so NE cancels and you get J equals to sigma E. Okay, this is the derivation. Okay, easy derivation. Next, derive an expression for drift velocity of free electrons in conductor. So here we have to derive the expression for drift velocity of free electrons in a conductor. Here we have, this question generally does not come, but sometimes it might come. We have a conductor through which you have applied some electric field and electrons started to drift in the opposite direction. Okay, so you have to find what the velocity of this electron when it is moving in this electric field. Now the derivation is actually very easy. How to do the derivation? Let's look into that. We know that whenever you keep a charge in an electric field, if you keep a charge in an electric field, it will experience a force, right? Any charge kept in an electric field will experience a force. What is that force? First chapter we discussed that the force is given by Q into E. So in this case, what is the force acting on the electric, if you apply external electric field E across the conductor, then only the electrons will drift, right? Now what is the force acting on the electron? So force acting on the electron is given by F equals to the charge of an electron times the electric field, right? E into E, that is a negative sign because charge of an electron is negative, so that's why minus E into E represents the force that acts on the electron, right? Now force we have calculated. Now again father equals to ma. Our grandfather Newton, he said that, grandfather of physics, okay. So from there we get father equals to ma. So from there we have to calculate the acceleration. So acceleration is E by m, where here m is the mass of electron, right? Here m is the mass of electron. Now so we have calculated the acceleration. It is basically a mechanics problem, not a electricity problem. Electricity problem is over as soon as you figure it out, right? Now we have to find that what is the velocity, right? So acceleration we know, initial velocity was 0 when it started. Its initial velocity, average initial velocity was 0. So we will use the formula that V d equals to u plus a t. Simple formula, u plus a t. So Vd is the drift velocity, so that is equals to, acceleration is minus E by m into time t. So this is the expression for drift velocity. Simple derivation, not much difficult. Only thing you have to remember, what are the steps? So steps is calculate the force, calculate the acceleration, apply first equation of motion, and then calculate the drift velocity. As simple as that. Now next question, charge through a cross section of conductor is given by Q equals to 2t square minus 5t coulomb. Find the current through the conductor at an instant t equals to 2 seconds. So Q is given, okay, and they asked you to find the current through the conductor. So how to do that? Current is basically given by dq by dt. This is the definition, right? We have learned in our theory section. This is the modern definition, okay. So we simply need to do, we need to just take the derivative of this, right? So it will be 4t minus 5, but that's not it. We have to find the current for time t equals to 2. So 4t minus 5 at t equals to 2, that is 4 into 2 minus 5, so that is 8 minus 5 equals to 3 ampere. So current is 3 ampere. Now next question, now it's a 5 marker derivation. So 3 marker questions are done. There was one more question that might come, expression, J is equal to sigma E from Ohm's law, which is I feel very easy. J is equal to sigma E, I thought I have included that question but not. So relationship between electric field and current density starting from Ohm's law. We did the same derivation, but we started from drift velocity. So there is a chance that might come as starting from Ohm's law, do the derivation of J is equal to sigma E. So that is very simple. If you have some difficulty in that, mention that in the comment section below. I will cover that in a later part of somewhat later, when we will be doing a lot of videos later on. So if you still have doubt on that, if you don't able to understand that derivation, that small derivation, that is also easy derivation, you can put that in the comment section below. I will include that in a future video. Two cells of different EMFs and different internal resistances are connected in series. Derive the expression for effective EMF and effective internal resistance of the combination. So here we have 2 cells. Generally they will give you 2 cells, not more than 2 cells, which is very simple. Okay, and whenever you draw that, you have to connect an external resistance. Okay, also I am going to teach you the shortcut method to solve the Wheatstone bridge in this lecture. So if you are still feeling bored, don't be bored. Yes, the topic is slightly boring, but the next topic is slightly difficult as well, but important as this one. Okay, both derivations are important, and the Wheatstone bridge as well. Wheatstone, there is a high probability that Wheatstone bridge will come not only for your midterm, but there is a possibility that it will come in your board exam as well. So don't skip it. Now series of cells is very easy. Okay, suppose the current in the circuit is I. Current in the circuit is I, and what is the from Kirchhoff's laws that the EMFs will be added. So from there we can say that current is given by epsilon 1 plus epsilon 2 divided by total resistance R plus R1 plus R2. Okay, simple Kirchhoff's law, total EMF divided by total resistance, nothing, or you can say Ohm's law only. Okay, Ohm's law, current equals to epsilon 1 plus epsilon 2 divided by R plus R1 plus R2. Very simple derivation. This series one is simple, parallel one is slightly tricky, but series one is very simple. If you get series one, you should consider yourself lucky. And in fact, some colleges I have seen, they give series as a 3 marker question, not as a 5 marker question. Okay, so that is also possible. So this might come as a 3 marker, not as a 5 marker. Now if you consider this is an equivalent circuit, now what is the main thing about equivalent circuit? Main thing about equivalent circuit, the current remains the same, everything remains the same. So what is the current in this case? Total, this is from the normal circuit, from equivalent circuit. So CKT is the short form of circuit. So from equivalent circuit, from what is the current? Current equals to total EMF. Total EMF, only one EMF is here, and divided by total resistance, that is R plus R equivalent. So this is equation number 1, this is equation number 2. Now if you compare these two, you can say that means comparing 1 and 2, comparing 1 and 2, epsilon equivalent is basically the same thing, epsilon 1 plus epsilon 2, and R equivalent must be this equals to this, equals to R1 plus R2. Okay, as simple as that, very easy derivation, 5 marks guaranteed if you just learn this. Very simple derivation. This derivation is easy. This one is slightly tricky. Derive an expression for effective EMF for internal resistance of 2 cells of different EMFs and internal resistance connected in parallel. So in this case they are connected in parallel. Now the main problem in parallel combination is that in parallel combination the current can be different, but the voltage remains the same. So epsilon 1, epsilon 2, R1, R2, and here again we have a resistance. Now current, say, through the resistance is I. So if you draw the equivalent circuit, equivalent will have only one. Now what is good about equivalent? Current in the circuit should be same. Okay, current through the circuit should be same. That is the main thing about equivalent circuit. Now what we are going to do, say current passing through this is I1, current passing through this is I2. Okay, so from Kirchhoff's current law, we can say I equals to I1 plus I2. Okay, so how to calculate I1 and I2? That is the major thing. So first we will consider this loop. Okay, this loop. So from this loop what we can say that epsilon 1 must be equals to I1 R1 plus IR. Okay. So from this we can calculate I1. So I1 equals to epsilon 1 by R1 plus IR by R1. Okay. Now what about I2? Similarly we can calculate I2 as epsilon 2 by R2 plus IR by R2. How did I do this? You have to take any single loop, okay, and then apply Kirchhoff's laws. Those who don't know how to apply Kirchhoff's laws, so you have to consider the current in a particular branch. This is called a branch, okay. This is a section of the circuit. This is not the complete circuit, this is a section of the circuit, so that's why it is called a branch. Okay, for example, if you consider, if you have studied SST in your class 10th, then geography is a branch of SST, history is a branch of SST, right? So that's how, similarly this is a branch of the circuit. Now the current through this is I1, so whatever current is passing from this circuit, the same current must come back to the circuit as well. That is the basic thing, conservation of charge. So if I1 current is passing through this, the same current will pass through this resistance as well. So according to Kirchhoff's voltage law, if the current is going in the direction of the battery, so battery or cell, if the current is going in the same direction, then the EMF of the cell is equals to the voltage drop across this resistance. How to calculate voltage drop? Ohm's law, I into R. Voltage drop is I into R. So here I1 R1, right? And but you have to take a complete loop, closed loop. So starting point, your starting point and your ending point has to be same. So you starting over here, so you are going over here, IR, okay, and then you are coming back over here, so I1 R1. So I1 R1 plus IR is the closing one loop. So from this loop you are writing this equation. We will solve numericals as well, where we will apply Kirchhoff's laws. So through that, I hope your Kirchhoff's law related doubts will be cleared. Now if you still have any doubts in Kirchhoff's laws, please mention in the comment below. I will make a separate short length video on Kirchhoff's laws. Now I1 we have calculated, I2 we have calculated. Now we will apply this law, that I equals to I1 plus I2, that is epsilon 1 by R1 plus epsilon 2 by R2 plus IR into 1 by R1 plus 1 by R2. Very interesting, isn't it? So what we have done, we have written this equation and we have taken this IR part separately. Okay, now what we are going to do, we are just divide both side. We will divide both side by this 1 by R1 plus 1 by R2. So we get I divided by 1 upon R1 plus 1 upon R2 equals to epsilon 1 plus epsilon 2 R1 R2 divided by 1 by R1 plus 1 by R2 plus I into R. Okay, what is the purpose of doing that? The purpose of doing that is to separate this IR term. It will be very, very helpful if you remember this trick. This is going to be helpful if you remember this trick. Now I think I don't have enough space, so I have to erase some of the text. So if you want the complete derivation, let me know. I will try to give you the complete derivation as well. Now I have to erase some of the texts over here. Now what we will do, we will be doing the same thing in the equivalent circuit as well. So if you consider the equivalent circuit, okay, I is total current, R equivalent is the resistance. So from there we will calculate again I equals to epsilon equivalent divided by R plus R equivalent. Now we will do the cross multiplication. So cross multiplication and we will get IR. I think I made one mistake. the mistake I made was, yes, mistake I made was there was a negative sign. This will be negative, right? I1 plus I2, I1 R1 plus plus IR was the equation, so that's why there is a small mistake. So this will be minus sign. I know many of you may have already commented by the time you see this, but yes, I have fixed it. So this is minus IR. So IR plus I into R equivalent equals to epsilon equivalent, or I R equivalent equals to epsilon equivalent minus IR, okay, or I divided by 1 by R equivalent equals to epsilon equivalent minus IR. Now if you compare these two equations, equation 2 and equation 1, what you will get? You will get this as simply, so basically if you see that here we have 1 by REQ, so 1 by REQ must be equals to this. So by comparing, this is slightly difficult and tricky derivation, whereas if you compare epsilon equivalent, this must be the epsilon equivalent, right? Minus IR is there, so epsilon equivalent must be equals to epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 upon R1 plus 1 upon R2. So if you remember this derivation, practice it 1 or 2 times. It will be very, very helpful for you to understand and remember the steps. The steps are very, very important and specific. If you try to solve it in some different way, that might not work. You may not be able to figure out how to compare it and what will be the value. So this is one of the simplest way to do the derivation. So arrive at the balanced condition of Wheatstone bridge using Kirchhoff's rules. So Kirchhoff's rules, so I am going to do this derivation at a very simple and easy way, the smallest possible way for this derivation. For that, what you have to do, you have to first mention that the two things. First thing is that the current through the galvanometer must be 0. Okay, current through the galvanometer must be 0. This is the galvanometer, okay, and because this current is 0, Ig is 0, that means I1 must be equals to I3. So current through this branch, this resistance is Q1, and I2 must be equals to I4. So again current through this branch is again I2. As simple as that. So first you mention that at balanced condition, Ig must be equals to 0, hence I1 must be equals to I3 and I2 must be equals to I4. So this is the first step that you have to mention. So once you have mentioned that, you have to take 2 loops and solve this question. So what is the meaning of loop? Loop means you start at some point and after going some multiple paths, if you end up at the same point, this is called a loop. A loop means where a starting point and ending point are same. So basically if you continue move on this, you will keep on going through the same process. This is called a loop, okay. So loop means starting point and ending point is same. So you are from college to home, from home to college is called loop. In between, if you sneak out and went for a movie, then you are breaking the loop. Don't go for a movie, you don't have the time. Now, so let's see. So you are first loop that we will consider. There are 2 loops that we will consider. One loop that we consider is this one. Okay, this one is the first loop, okay, and second loop we will consider this one. So these 2 loops we will consider, okay. So so this is our loop 1, this is our loop 2, Okay, first loop starting here, going here. Now current through this is 0, current is 0 over here. Okay, so this is my loop 1, this is my loop 2. Now what we will do, we will apply Kirchhoff's voltage law. Applying Kirchhoff's voltage law at loop 1. Okay, if you draw the diagram like this, it will be very helpful for you. You can directly mention the way I am writing, you can write it like exactly like this. So I into P, I into R. So first we are starting here, starting point, we are going through a resistance, we are going through a resistance. So if you are going through a resistance, the value of the resistance times the current, that is the voltage drop. So value of the resistance times current is the voltage drop. Okay, so this is the voltage drop across this. Now there is no voltage drop across this because there is no current in this, so we can simply consider that there is no current. So we will directly go through here, and then we will go in this direction. Okay, from this point to this point, R into I2. Now if you see that our loop, the path that we are following is going in this direction to meet at our starting point. So we are going from A to B to D to A, B, D, A. So we are going from, starting from A, we are going to B. So when we are going from A to B, the direction of current and our chosen direction and the direction of current are in the same direction. So that means this is positive. Now you, from B to D no current is there, so directly you can come over here. Now D to A, when you are going from D to A, okay, our chosen direction is opposite to that of the current shown in the circuit. Why? Now you might say, sir, current in the circuit might go in this direction. That is not possible because of the battery. So battery will try to send the current in this direction only. So that is why the current originally will try to go in this direction, but our loop, to close the loop, we have to go in the opposite direction of the current. So if we are going in the opposite direction of the current, then there will be a negative sign. So it will be R into I2. And is there any battery connected in this loop? So if you see this particular loop, no battery is involved over here. So if no battery is involved, that means it will be equals to 0. Okay, or we can say P I1 equals to R I2, or I1 by I2 equals to R by P. Okay, so now we will apply the same KVL, applying KVL at loop number 2. Now loop number 2, you can take starting point is now B. So B to C to D to B. So when we are going from B to C, we are going in the direction. So I1 into Q, or Q into I1. Okay, why we are taking I1? Because I1 and I3 are equal. Okay, so Q into I1 minus, again from C to D we are going opposite direction of the current. Current in this circuit is going in this direction, right? This direction is wrong, by the way. So current is going in this direction. So C to D we are going in the opposite direction. So we can write this as S into I2 equals to 0. So from here we can write I1 by I2 equal to S by Q. Okay, now comparing equation number 1 and equation number 2, we can write R by P equals to S by Q, or just do some cross multiplication, P by Q equals to R by S. This is the common form of Wheatstone bridge. Very simple, easiest derivation. No complication, not difficult. Okay, this is the easiest derivation of Wheatstone bridge. Now let's move on to the numerical questions. You can expect at least one numerical. Now circuit diagram based numericals are common from this chapter, but in some cases some other forms of question might come, so those questions are also included in this session. So number density of free electrons in copper is estimated to be 2 into 10 to the power of 28 per meter cube. A copper wire of length 3 meter and area of cross section 2.0 millimeter square is carrying a current of 6.4 ampere. Calculate the drift velocity of electrons. How long does an electron takes to drift from one end to the other end of the rod? So let's see. So first of all, I equals to NEA VD. Okay, so VD is basically I by NEA. So I is given here 6.4 ampere. Number density is given 2 into 10 to the power of 28. Charge of an electron we know 1.6 into 10 to the power of minus 19, and area of cross section is 2 millimeter square. 2 millimeter square means 2 into 10 to the power of minus 6 meter square. Okay. Millimeter means 1 millimeter means 10 to the power of minus 3 meter. Millimeter square means 10 to the power of minus 3 whole square. So whole square, that's why 2 into 10 to the power of minus 6. Now let's simplify this. So it will be 3.2, it will be 2, cancels 1. So 1 divided by 10 to the power of 28. Minus 19 means 10 to the power of 9, 9 minus 6, 3. So 10 to the power of 3. So it will be 10 to the power of minus 3 meter per second is the drift velocity. So this is the expression for drift velocity, right? Very simple. Just put the values. You know the equation, put the values and calculate it. Now second part is interesting. How long does it will electron will take to drift from one end of the wire to other? So basically electron is going through this 3 meter long wire. It is starting from this end. How much time it will take to drift from here to here? That is the time, that is the thing. So for that, what you have to do, the drift velocity you have calculated, distance you know, so time equals to distance divided by velocity, right? So distance is 3 meter here, so 3 divided by 10 to the power of minus 3, that is 3 into 10 to the power of 3 seconds. Okay, so this much time it will take to drift from one end of the wire to the other end of the wire. So 10 to the power of minus 3 meter per second is the drift velocity. But very important thing is mentioning the units. If you don't mention the units, you will not get any, the marks will be deducted. I will not say you will not get any marks. When I was the student, if you don't mention the units, complete marks will be not given. You will get 0. Nowadays the teachers and the community is little more lenient, so they will only deduct 1 marks. But in our case, when I was the student, if you don't mention the units, you will get 0 marks. Next, in the following network, find the current I3. So you have to find this current I3. I taken this question from your sample paper, last year sample paper. So let's understand this. So if you see this circuit diagram, currents, initial currents are given, the EMF is not given, but the current that coming into the circuit which is given. So 1 ampere current is going in, okay, and it is dividing into 2 branches. One current is I1, another current is I2. So if I1 current goes here, the same current must go through this as well. So and I2 current must go through this as well. Now I3 current is passing through this intermediate resistance. So what will be the current through this? So current through this will be I1 minus I3. So entering to the circuit is I1 at this junction, exiting must be equals to the same. So if I3 current exit in this direction, then I1 minus I3 remaining current must exit through the other resistance. So this is very, very important to understand when you are doing circuit analysis. Circuit analysis means, so you have to check, okay, at this junction I1 current goes in, I3 current goes out. So remaining I1 minus I3 current must go through this. So for example, if say 5 ampere current goes in, 2 ampere goes out, that means there are extra 3 ampere current. So that 3 ampere current must go through the other resistance. This is how you figure it out. Now at this junction, if you observe, this is a junction. Junction means where multiple resistances meet. Okay, at this junction, if you see that, in fact, they have also mentioned this current as well. Anyway, so if I2 current is passing through this, I3 current is passing through this, that means current through this resistance will be I2 plus I3. Okay, it is mentioned over here. Anyway, now, so we have figured out the currents. Now we will be applying KVL to simplify and solve this circuit. So first of all, what is the first point? Kirchhoff's current law. So from Kirchhoff's current law, I1 plus I2 must be equals to 1 ampere. Because 1 ampere current goes in and I1 and I2 current goes out, that means sum of outgoing current should be equals to sum of incoming current. So from there we can say that I1 plus I2 must be equals to 1 ampere. Now we will take two loops. Okay, we have to find the current I3. Our target is to find the current I3. Okay, so we will take this loop. Okay, we will take this loop, and if required, then we will take the other loop. So we will start with one loop and we will see that if we can solve this question or not. So if we take this loop, loop means starting point and ending point must be same. So say this is loop number 1 and this is loop number 2. If required, then we will take the loop number 2. If it is not required, we will not take. Anyway, let's see. So if you apply Kirchhoff's voltage law, at loop number 1, we get, so first we started from this point, resistance times current. Okay, so 10 I1. So this is our first resistance, first station. Next station is 5 ohm and current through this is I3. Now are we going in the direction of current? So from here to here we are going in the direction of current. From here to here also we are going in the direction of current. So it will be plus. That is 5 I3. Okay, 5 I3. Now from here to here, our last station we are going through this 20 ohm. Now for last station we are going in this direction, but current in the circuit going in the opposite direction. That means it will be negative I2 into 20 or 20 I2. 20 I2. And if you see that in this circuit no battery is connected, so that means it should be equals to 0. Okay, it is not necessary that battery has to be connected when you are considering Kirchhoff's voltage law. That's why it is more important and more useful than Ohm's law. In Ohm's law, this is basically an extended Ohm's law, you can say, and a much more generalized version of Ohm's law. Okay. So this is how you can see. Now you see that we have two equations, equation number 1 and equation number 2. Now if you see that we have three variables, I1, I2, I3, but we have only two equations. So two equations, three variables are not solvable. So you have to have at least 3 equations to solve 3 variables, which is very, very important. This is a mathematical principle. The number of variables must be equals to number of equations. So if you have 3 unknowns, then you must need 3 equations. So here we have 3 unknowns but 2 equations, that is not solvable. So what we will do, we will be apply the KVL for loop number 2 as well. So applying KVL for loop 2. Now you tell me. So we are starting from this point, we are going in this direction. So are we going in the direction of current? So current through this resistance, current coming over here. So current must be going in this direction. Yes, we are going in the direction of current. So what is the resistance? 10. What is the current? I1 minus I3. Okay. So this must be positive. Now we reached this point. Now again current in this case is going in this direction. So we are going to reach from here to here, we are going in the opposite direction. So if we are going in the opposite direction means this must be negative. So it will be minus 5 I2 plus I3. Okay, and again after this point we are going in this direction, again opposite to the current. So opposite to the current means I3 into 5, that will be minus. So minus 5 I3, and it will be equals to 0. No battery is connected, that means it will be equals to 0. Now little simplification. So 10. Now the answer to this question is not pretty. Okay, slightly tricky. But this question is given in your model question paper. Okay, so it will be 10 I1. Now if you are good in solving variable based questions, then it should be very easy for you. 20 I3 minus 5 I2 equals to 0. Okay, so first equation is I1 plus I2 equals to 1, or I2 can be written as I1 minus I1, right? Now what is the second equation? Second equation is 10 I1 plus 5 I3 minus 20 I2. So 10 I1 plus 5 I3 minus 20 I2 equals to 0. Now we will put that value of I2 in this equation. So 10 I1 plus 5 I3 minus 20 into 1 minus I1 equals to 0. So it will be 10 I1 plus 5 I3 minus 20 plus 20 I1 equals to 0. So just simplify, you will get 30 I1 plus 5 I3 equals to 20. Now divide everything by 5. 5 6 just 30 plus 1 I3 equals to 4. So this is another equation, equation number say 4. Now we will put this equation into our equation number 2, equation number 3. Equation number 3. Okay, so 10 I1 minus 20 I3 minus 5 I2. So 10 I1 minus 20 I3 minus 5 I2 equals to 0, or 10 I1 minus 20 I3 minus 5 into 1 minus I1 equals to 0. This is from equation number 2. This is equation number 3. Now if you simplify, this will be again 15 I1 minus 20 I3 will be equals to 5. Yes, 5. Again we can divide this by 5, and we can write this as 3 I1 minus 4 I3 equals to 1. Okay, if you divide this 5 each number, you will get this equation. Now we are trying to find I3. So what we will do, we will multiply this equation by 2. Okay, this is number 5. So we multiply this equation by 2 and then we subtract it. So first we will write this. Okay, 6I1 plus I3 equals to 4, and then multiply this with 2. 6I1 minus 8I3 equals to 2. Okay, now what we will do, we will subtract. Okay, so we get cancel 9I3 equals to 2, or I3 equals to 2 by 9. Okay, I think some mistake happened over here. It is 2 by 9, not 8 by 9. Okay, in case I make some mistake, please let me know. It's perfect. Okay, it will be 2 by 9, not 8 by 9. Okay, next question. 3 resistors, 2 ohm, 3 ohm, 6 ohm are combined in parallel. What is the total resistance of the combination if this combination is connected to a battery of EMF 2 volt and negligible internal resistance? Determine the current through each resistor and total current drawn from the battery. So 3 resistors combined in parallel. So we have a 2 ohm, a 3 ohm and a 6 ohm. Okay, they are all connected in parallel. So 2, 3 and 6, they are all connected in parallel. What is the equivalent resistance? So equivalent resistance can be calculated as R equivalent equals to 1 upon 2 plus 1 by 3 plus 1 by 6, right? This is the formula, easy, and you can do this by 6, 3 plus 2 plus 1, that is 6 divided by 6, that is equals to 1. So R equivalent equals to 1 ohm. Okay, so equivalent resistance for this is 1 ohm. Now what you are doing, you are connecting this circuit to a battery. So you are connecting this to a 2 volt battery. Now you have to find the current through each resistances, I1, I2 and I3. Very easy, very easy. You take any one of the loops and apply KVL. Okay, so you take this loop, only one resistance, I1 into 2. So 2I1 must be equals to the battery. Only one loop, so you are starting here, you are taking the simplest possible loop. So I1 equals to 1 ampere. Okay, now you take the second resistance. Second resistance, same thing, second resistance. 3I2 equals to 2, so I2 must be equals to 2 by 3. Okay, and now you take this last loop, I3, okay, and this is 6, so I3, 6I3 equals to 2, or I3 equals to 1 by 3 ampere. Now unit is very, very important over here. Now total current in the circuit is basically I1 plus I2 plus I3, that is 1 plus 2/3 plus 1/3, that is 2 ampere. Okay, so I think answers are not mentioned here. Next question, for copper the number density of free electrons is 8.5 into 10 to the power of 28 per meter cube, and resistivity is 1.7 into 10 to the power of minus 8 ohm meter. Calculate the conductivity of copper and relaxation time of free electron in copper. Take the mass of electron as 9.1 into 10 to the power minus 31 kg and charge of electron as 1.6 into 10 to the power of minus 19. So resistivity is given. Okay, so resistivity is given as 1.7 into 10 to the power of minus 18, and also the number density is given 8.5 into 10 to the power of 28. Okay, so first of all we have to find the conductivity. Conductivity is simple. Conductivity is nothing but 1 upon resistivity, which is equals to 1 by 1.7 into 10 to the power of minus 18, or conductivity is 10 to the power of 18 by 1.7. Okay, so if you take, it will be approximately 10 by 1.7, which will be approximately 6 point something, okay, into 10 to the power of 17. Okay, you can calculate it using a calculator, exact value, right? You have the calculator, but I am not interested in the calculator. Now next part is what you have to calculate: the relaxation time. Relaxation time of free electrons in copper. So for that, what you have to remember that the conductivity is related to relaxation time using this formula, Ne square tau by m. Okay, this is the formula for conductivity and relaxation time. So from this equation you can calculate the relaxation time. So relaxation time is conductivity into mass divided by number density into electrons charge square. So conductivity we have already calculated, 6 into, you can use the exact value, 17. Mass is given by 9.1 into 10 to the power of minus 31, okay, divided by number density n is 8.5 into 10 to the power of 28, and charge of an electron is 1.6 into 10 to the power of minus 19 whole square. Okay, so this is slightly a mathematical question, and if you solve it you will get that. Okay, one mistake I made is this is not 10 to the power of 18, this is 10 to the power of 8. Okay, 10 to the power of 8. So it will be 10 to the power of 8 by 1.7, and it will be 6 into 10 to the power of 7. Okay, so what I have done, by the way, if you are still thinking, sir, how did you do that? What I have done this 10 into 10 to the power of 7. So 10 to the power of 8 I broken into two parts, 10 and 10 to the power of 7, and then I divided it by 1.7, which will roughly come up to be a 6. Okay, so this number is roughly to be 6 and then 10 to the power of 7. And if you put these values and calculate it, you will get this as I am saving myself from a difficult calculation. If you have a calculator, you can calculate it. This is a board exam, so small simple calculator is allowed. So this multiplication and 10 to the power of calculation you have to do it, and you will get this as your answer. Now next question. Two cells of EMF, this is the last question of the day. Two cells of EMF 2 volt and 3 volt each having internal resistance 1 ohm are connected in parallel combination so as to send the current in the same direction. So both are two cells are connected in parallel and they are sending the current in the same direction. What is the meaning of that? That this is a simple question, not a difficult one. Okay, so this is how they are connected. So they are sending the current in the same direction. Calculate the equivalent EMF and equivalent internal resistance of the combination. Equivalent EMF we already derived it. For parallel combination, epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 upon R1 plus 1 upon R2. So let's see the values. 2 divided by 1. So each of them have internal resistance 1 ohm, plus 3 divided by 1 divided by 1 upon 1 plus 1 upon 1. So it will be 5 by 2, which is 2.5 volt. So this is the equivalent EMF. R equivalent is given by R1 R2 by R1 R2, R1 plus R2, two resistances in parallel. So parallel resistance formula, right? So 1 into 1 divided by 1 plus 1, that is 1 by 2, that is 0.5 ohm. Okay, so this is the R equivalent. Now next is, if this combination is connected across an external resistor of resistance 2 ohm, then determine the terminal potential difference across the resistor. So now we can consider this circuit to be an equivalent EMF circuit. Okay, we have already calculated the equivalent EMF. So this is epsilon equivalent, this is R equivalent, and 2 ohm that we have connected this. Now we are trying to find the terminal potential. Terminal potential, to calculate terminal potential, first we have to calculate the current and then multiply current into resistance, we will get the terminal potential. Okay, so first what is current in this circuit? Current in this circuit is the EMF divided by total resistance. So R plus R eq. So now put the value. So I equals to 2.5 divided by 2 plus 0.5. 0.5 ohm, right? So it will be 2.5 divided by 2.5, that is 1 ampere. So what is the terminal potential? Terminal potential is current into resistance, external resistance. So that will be 2 into 1, that is 2 volt. So 2 volt is the terminal voltage. Now this type of question has also started to coming from this chapter. If you see this kind of questions, don't ignore it. If you remember this formula, this is a very easy question. Okay, so combination of cells related question, if they are coming, try to figure out the circuit diagram and then apply the formula. It will be very simple compared to the circuit diagram related questions, where if you just miss one sign, positive, negative, your total marks will be gone. Okay, so circuit diagram related questions you can avoid, but if you are solving simple other style of questions, you should solve it, because those are basically a formula related question, right? I hope this helps. Yes, this is the answer. And if you have not yet subscribed to our channel, don't forget to subscribe to our channel, and obviously share this video with your friends and give it a thumbs up if you like this video. Also join the WhatsApp channel where our class notes will be shared. I will be back with a new chapter very soon. Till then, bye.